Okay, we're interested in finding out what the pressure is as a function of position underneath a fluid. So pressure due to fluid statics as a function of position. Now, from our basic physics, looking at a Navier-Stokes equation or just an argument about the weight of water, and we'll assume that this is water in all of these cases, so density of about 1,000 kilograms per cubic meter for the sake of round numbers. We know that as we go beneath the water, the pressure increases and that delta P is equal to rho G delta H. So if we're using gauge pressure and we start with a pressure equal to 0 at the surface of the water because it's exposed to atmospheric pressure, then the pressure will increase as we go down. So at this point, P will be equal to P at the surface, which is just 0, plus rho G delta H, which is just this distance H here. So P is equal to rho GH. That's an easy one to figure out. If we made our coordinate system such that it started at 0 and increased positively in this direction, then H would be that coordinate, and writing the equation would be easy. But often we need to put our pressure in terms of other coordinate systems. For instance, if we're already working with a coordinate system that has y positive upwards with the origin at the surface of the water, then obviously as y goes negative, P is going to become positive. And that's a fairly straightforward transformation of coordinate systems from here we have H, there we have y is negative H. So P is equal to rho GH or rho G negative y, or negative rho GY. That's pretty straightforward to get it in terms of y. Now, suppose we had y down starting here, we'd have a constant added in there instead of the 0 that we had here when we did that transformation to y. But otherwise, these transformations are fairly straightforward if the axis is aligned with the change in elevation, the height axis. When would we not align the vertical axis y with the vertical axis of gravity? If we were trying to figure out the pressure force acting on a surface here, so pressure always acts perpendicular to the surface, and actually I've drawn that wrong. The pressure is going to be increasing in magnitude as we go down below the water. So there's a higher pressure down here and a lower pressure up there. If we were interested in integrating this distributed pressure force over some surface that was here, maybe a trap door in this wall, then we'd need to be able to express pressure in terms of the x dimension. Now, because this is a linear relationship, this is a straight line, we're just going to wind up with pressure equal to some constant plus some other constant times x. And the pressure is going to be decreasing as x increases, so d is going to wind up being a negative number. So if we're this distance under the water, let's call that 10 meters, then the pressure will be rho g times 10 meters. That's the pressure here. And it will decrease as we move along in increasing x as we increase our height here. So we're interested in what is this height here, this rise, in terms of the progression in x. if that's an angle theta, then this is x times sine theta. And sine theta will be a constant that we'll know from the geometry. So rho g times 10 is the constant here, where x is equal to 0, plus rho g, the change in the depth under the water is negative x sine theta. We're moving up. As we have an increase in x. So P will wind up being equal to rho g times 10, our 10 meters under the water, minus rho g sine theta all times x. So a linear relationship where these things are constants. And that'll be really easy to integrate when we go to try to find out that force. If things get a little more complicated, we may want to be a little more careful about how we align our control surface with our coordinate system. If I've got a cylindrical surface like this, it might be a curved gate that's cylindrical, and I want to know what the pressure is on the surface of that gate, I could do it in terms of position theta. So I could start off, I'm still at 10 meters down here, so my pressure is going to be at 10 meters down when theta equals 0. I'll have rho g times 10, and the pressure is still going to decrease with increasing theta, so minus rho g times the elevation here for that angle theta that we've transferred through. So if I again look at the same triangle, if the radius here of this circle is r, then that elevation is going to be r times cosine of theta. So it'll start when theta is equal to 0, or sorry, no, sine of theta. R times sine theta. So here theta equals 0, elevation is 0, that's increasing, and we'll have r, rho g r, sine theta. And in this case, over here theta was a constant, but over here theta is one of our coordinates. And we can integrate around there using theta as our coordinate. If we wanted to make our life more complicated, we could try to put it in terms of y and x, and that integration would wind up needing double integration over both dimensions. So rearranging this, pressure equal to rho g times 10 minus r sine theta. So all of these are just exercises in geometric transformations. They're fairly straightforward, but you need to practice them a little bit. The main thing is establish an initial datum point where whatever coordinate system you're working with is at its 0 point, and that'll tell you what the constant is for the pressure. So the pressure is always going to be the pressure at the datum plus some delta P from that datum that's going to be a function of the coordinate direction that is best suited to mapping out the surface that you're trying to follow. And that'll allow you to get a relationship for pressure as a function of the coordinates you'd like to integrate over. Because once you wind up integrating to get a force equal to the integral over an area of the pressure times the unit normal vector acting inwards, integrated over the area. You'll need to be able to do this integration. You'll need to have that as a function of the coordinates that define the area that you're integrating over. So, basic mathematics of transformations, transforming coordinate systems, fairly straightforward, but sometimes a little difficult to do on a quiz or an exam under pressure. So try some test cases first before you go into an exam.